Hi kids, video 19 is on forces and free body diagrams. This is a really video that's full of a lot of information, so please listen to this with the sound on and pause the video to take careful notes because there's a lot of crucial details in this video. The essential question is, how do you determine the size and direction of individual forces and whether they are balanced or unbalanced on an object? So there's a handful of specific forces that you should be aware of. As I mentioned earlier, we'll identify all of these by the subscripts under the letter F to show they're all forces, but they have different kinds of names. I would make this table in your notes and go through the 5 most common specific forces that we're going to be talking about. The first is the force of gravity, and we'll use an F sub g to represent the force of gravity. Gravity acts between any 2 objects with mass. You're probably used to thinking about gravity acting on all the objects on Earth, which is true, but the reason that gravity acts on every object on Earth is because every object around us has mass, and the Earth also has mass, and so we would actually, in physics, more accurately say gravity acts between the Earth and all the objects on Earth, instead of just thinking about a force that is only acting on the things around us. We're not going to give you the equations for all of these forces, but we do want you to be familiar with some of the relationships that cause these forces to be large or small, depending on the properties of the object. So objects that have a lot of mass have a lot of gravity acting on them. That should make sense, like the piano or the desk has a lot more gravity acting on it than the pen or pencil. And if Earth had heavier mass, then we'd all be experiencing more gravity as well. So there's a linear relationship between mass and gravity, and there's also an inverse relationship between gravity and the distance between objects, which is the reason why we're not all being pulled to the sun, which has more mass, but it's a lot further away. So the gravity from the sun is a lot smaller than the gravity from Earth that's acting on us. Another thing to talk about is the direction of these forces, which you can usually predict if you understand something about the forces. Gravity, we say, is always an attractive force, and another way to describe that is by saying that 2 objects are always pulled towards each other. So you often think of gravity acting down, but you understand that somebody on the other side of the planet would experience gravity up. That's because no matter where you are being pulled towards the Earth, and the Earth is actually being pulled towards you, but we'll talk about that more in another video. So gravity is a super important force. Every object on Earth is going to be experiencing gravity because of the Earth. The second force is actually feels like a lot of different forces, and that's why it's called the normal force, because it's actually most of the forces acting on us every day are actually this force. And we use an F with the sub n to represent normal force. Now, normal force acts between any 2 objects that are in contact. So if you look around you or you think about yourself, all the things that you're touching, every single one of those things that's touching you is actually called a normal force. And the normal force depends on how much pressure there is between the 2 surfaces that are in contact. So you probably have a lot of normal force right now from your chair that's holding you up, and a little bit of normal force from your pencil or your clothes or other little small things that are touching you. Normal force, we would say the direction of the normal force, objects experience normal force away from each other, which means, like for the chair, for example, the chair is pushing up on you. It's pushing away from itself, and you are pushing down on the chair. So each of you would be experiencing a normal force away from the object that's pushing on you. The third force is friction, which is F sub F. And we've talked about friction a little bit already and how important it is in transforming energy. Friction is all around us, of course. Every time 2 objects rub against each other, they experience the force of friction. And the relationships that determine how much friction an object experiences are how rough the 2 materials are. That's a linear relationship. So the rougher the materials as they're rubbing, the more friction they have. And also the normal force, which we just learned about. So in other words, the harder the pressure is between the 2 objects, the more friction they experience. You can notice this force yourself if you put your hand on your desk and kind of pull it across the desk. If you then put more pressure between your hand and the desk, so kind of push down on your hand as you pull it, you'll notice the friction actually goes way up. It's much harder to pull your hand if you're squishing those two surfaces towards each other. The direction of friction is always opposite from the direction the objects are moving. So when you're pulling your hand towards you, it experiences friction away from you. The fourth force is called tension, or F sub T. And tension force is a force between two objects that are connected by a string or a rope of any kind. And the relationship that determines how much tension something has is just how hard the string is pulled. So if you're pulling on a string gently, then there's a little bit of tension force. If you're pulling really hard, it's going to be a lot. The direction of tension is always along the direction of the string, so whichever way the string is pointing is the direction that you experience tension. So tension can only pull, you can't push with a string, so and you can't pull sideways with it either, so we'd say the direction is always along the direction of the string. And the last force is not one we're going to be talking about much during this unit, but we will when we get to our next unit, which is the force of electricity, or Fe. And Fe is a force that acts between any two objects that have a property called charge, which you may have experienced when you scuff your socks along the carpet or pull something out of the dryer or go down a slide, right? So it's actually a very strong force, but it comes into play in very specific times. The relationships that determine the force of electricity are the amount of charge the objects have, and again, similar to gravity, how far apart those objects are. Electricity is an interesting force because it can either be attractive, which means pulling two objects together, or it can be repulsive, which means pushing the objects apart, and we'll learn more about those specifics when we get into our electricity unit. So there's a very important tool we're going to be using in this unit called a free body diagram, sometimes abbreviated FBD. A free body diagram is a picture of an object, or it could be a system of objects, and the forces that are acting on that object or system. The reason we use free body diagrams is because you can really quickly tell when you look at a free body diagram if the forces on that object are unbalanced or balanced. And this matters because this is going to tell us whether the object is accelerating, as it would be if the forces are unbalanced, or not accelerating, as it would be if the forces were balanced. Remember when we had that equation for acceleration and the linear relationship was sigma f? So sigma f is basically the total amount of force, and if the total amount of force is unbalanced, so there's a number there, the object accelerates. If the total force is 0, then we would say it's balanced. We're not going to be accelerating. This is a big deal in physics because oftentimes we can tell a lot about the forces acting on an object, and we want to use this information to make predictions about what's going to happen to objects over time. So if you understand free body diagrams, you can kind of tell the future in terms of the movement and motion of objects. So I'm going to run through a couple examples of free body diagrams. But the free body diagram itself that you draw is unique as the object that you're drawing it about is. So this is just an example of a balanced free body diagram, but there's lots and lots of free body diagrams that you could draw that would be balanced. Whenever you draw a free body diagram, the object that you're drawing it of is going to be represented by a box, no matter what it looks like. And the forces acting on that object are represented by arrows. The arrows are going to be pointing in whatever direction the force is acting, and the length of the arrows should show roughly how big the force are, so a bigger arrow for a stronger force. Every arrow that you draw should be labeled with the type of force, and ideally the name of the object causing the force. So here's an object, a very interesting object, an ostrich standing in a field. If I wanted to draw a free body diagram of it, the first thing I would do is draw my box that represents the ostrich. And then I'm going to add all the forces. Usually the first force I put on every free body diagram, assuming that we're on Earth, is the force of gravity. We know that that force is going to pull the ostrich towards the Earth. So I'm going to draw that arrow downwards and label it FG with a little parentheses Earth, because I want to show that this is a force caused by the Earth. Now if I think about the ostrich, the only other force acting on that ostrich right now is the ground that's pushing up on it. And that is an object in contact force, which means it's a normal force. So I would label that Fn for a normal force caused by the ground. Since this object is just standing still and not accelerating, that tells me that the forces on it are going to be balanced, right? We've got zero acceleration, its velocity is not changing, which means that sigma f, or the total forces, have to be also equal to 0. And what that means is that the up and down forces are equal to each other, so that they can basically cancel out to 0. Sometimes when two forces are equal to each other, it's handy to draw these little cross marks, tick marks across them. It's kind of a way of representing really quickly to show that you know that those two forces must be equal to each other. And that's it. That's the free body diagram. Pretty straightforward. There's one little note about balanced free body diagrams, and that is that you should remember that objects that have balanced free body diagrams are not necessarily at rest. This ostrich is, but all that you can tell from a balanced free body diagram is that the object is moving at a constant velocity, which is 0 acceleration. So this ostrich could have the exact same free body diagram if it was, for example, riding in a train that was going across the ground at a constant velocity. The exact same free body diagram would be true even though that ostrich is moving. The forces would be balanced as well. Okay, let's run through an example of an unbalanced free body diagram. This is a baseball player. His name is Bryce Harper, and he's sliding into first base. So when I draw the free body diagram, I'll start off with my box. I'm going to go ahead and put in the force of gravity again, downwards onto Bryce from Earth, and the normal force from the ground that is acting upwards. Those two forces are balanced because Bryce is moving at a constant velocity up and down, right? He's not accelerating up into the air or down through the earth, so those two forces are balanced in the up and down direction. There's one more force that belongs on this, and that's the the friction force acting on Bryce. And the friction force is caused by the dirt that he's rubbing against, and the direction is always opposite from his motion, so he's moving to the right there, so I'm going to put a friction force acting to the left. And that force is unbalanced, which means that he is accelerating in that direction, right? So I just mentioned this, but I'll reiterate it. The up and down forces are balanced because there's 0 acceleration in the up and down direction, which means that sigma f and acceleration are both equal to 0. So there's no acceleration up and down. However, sideways, side to side, those forces are unbalanced. There's only one force in this case. It's the force of friction. And that means he's going to be accelerating in the direction of that extra force. So he's going to be accelerating to the left because that's the only force acting on them in the sideways direction. So in this case, sigma f on Bryce would be the same as the value of the force of friction. If you add up all those forces, what's left over is just that ff. So when we use that Newton's second law equation, A equals sigma f over m, we could determine that the acceleration is equal to the force of friction over m, because the force of friction is the only unbalanced force in this scenario. One common mistake with unbalanced free body diagrams is that people tend to think that if there's an unbalanced force, that must be the direction the object's moving. Even in the example we just came up with here, that's not the case, right? He's moving to the right, and there's an unbalanced force to the left. So just a reminder that velocity and acceleration do not have to be in the same direction. Sometimes they are, and sometimes they're not, but you can't always tell which way an object is moving just from looking at the free body diagram. So the last slide, I just want to talk about what can we do with free body diagrams and what can't we do with free body diagrams. This is kind of revisiting some of the common mistakes from the last couple slides. What we can do, if you know all the forces and the mass of the object, you can find the acceleration using Newton's second law and adding up all the forces that you see in the free body diagram. This also lets us figure out how much velocities of objects are going to be changing over time. Or, from the other end, if you know the acceleration of an object and you know some of the forces, this actually lets you determine the value of the other forces. So you can go either direction, and we'll be doing that in a future video. What can't you do with free body diagrams? Well, unless you actually know how fast it's going from the beginning, you can't actually tell if it's speeding up or slowing down or even what direction it's moving if the only information you have is the free body diagram. Please remember that the direction of the acceleration is not always the direction of the motion. And that positive acceleration isn't always going faster, negative isn't always going slower. I know we talked about this a long time ago, but I'm sure it'll come back as we get into it in this unit. Okay, so there was a ton of information. It would be really, really useful for you to go back and highlight the things that you thought were super important, underline things, write a quick summary. The essential question was, how do you determine the size and direction of individual forces and whether they are balanced or unbalanced on an object? And hopefully you have good notes on this one because it's really going to help you in class. Thanks for watching.